Okay, so we will discuss the Miller-Rabin primality test. So this is, in some sense, a refinement of the Fermat primality test. And we start with a natural number, presumably an odd number. So let n in n be odd. And we ask, is n prime? So basically, we have a series of conditions. These are congruence conditions. And they're based on choosing a number a, which is greater than or equal to 2, and less than or equal to n minus 1. So we take this number a, and then we proceed to write n minus 1, which is now an even number, as 2 to the r times m, where m is odd. And we pose the following questions, one after the other. Does n divide a to the m minus 1, which is equivalent, of course, to asking if a to the m is congruent to 1 mod n. Does n divide a to the 2m I'm sorry, a to the 2m plus 1? Again, it's the same thing as asking whether a to the 2m is congruent to negative 1 mod n. And we go all the way to n dividing a to the 2 to the r minus 1 m plus 1, which is the same thing as asking whether a to the 2 to the r minus 1 times m is congruent to negative 1 mod n. If the answer to one of these questions is yes, so the moment we find a yes, if we get a positive answer, then n passes the test. And here we can find different pieces of terminology. Sometimes we will say with witness A. So this does not mean that it is a prime number, but it simply means that it may be a prime number. If for a given A, n fails all of the above conditions, then it is a composite. So the status of the Miller-Rabin test is a probabilistic test. So usually in practice, we try to perform it for a number of witnesses. And if it passes for all of these witnesses, then we label our number as a strong probable prime number. Okay, not as a prime number, but a number which could be a prime number with strong probability. And that's it. Thanks for watching.